Thanks for the invitation. I'm so sorry I cannot attend this workshop in person because there's a problem with my visa. So my name is Junpeng Jiao. I'm from Yale Mathematical Science Center, Tsinghua University. Uh, Title of my talk is the boundedness of SLC degenerations of polarized log-Calabi pairs. So according to the minimum model program, algebraic varieties can be classified in terms of three main building blocks that generalize the Riemann surface of genus greater or equal to 2, equal to 1, and equal to 0 to a higher dimensional context. And there are many reasons to study log pairs. A log pair is a variety with a divisor on it, instead of just varieties. For example, the degeneration of Calabi varieties naturally leads to a log Calabi pair. So among all the log pairs, the following three types of log pairs is particularly interesting. So let XB be a projective log canonical pair. If you are not familiar with the language of log canonical, you can consider it as a smooth variety X with a simple normal crossing divisor B on it. And the coefficient of the B is between 0 and 1. We also call this divisor on its boundary. We say XB is log general type if Kx plus B is big. We say XB is log Calabi if Kx plus B is Q linearly equivalent to 0. We say it's log final if negative Kx plus B is ample. In algebraic geometry, degeneration is taking a limit of a family of varieties. So precisely given a flat morphism of variety to a curve f with orange 0, then the fiber xt form a family of varieties over C. Then the fiber over 0, x0 may be thought of as a limit of xt as t goes to 0. One then says the family xt degenerates to the special fiber x0. A family of variety is easy to define, but for log pairs, things may be difficult because of the boundary, the divisor. So we define a family of projective log pairs. It's an object f x xb to c. It consists of a morphism of varieties f and an effective q divisor delta on it, satisfying the following properties. First, f needs to be projective, flat or finite type, and of pure relative dimension d, with geometrically reduced fibers. This is the same definition with the family of projective varieties. And for the boundary part, for the divisor B, we need every irreducible component of the divisor dominant C, and all fibers have pure dimensional d minus 1. And we also need to assume f is smooth at the generic points of every component of the intersection of xt with every component of the boundary, and it's for every point. Degeneration. When we study degeneration of varieties, there are many reasons to study degeneration. One reason is to compactify the modular space. In this talk, we are particularly interested in the Calabi variety. And compactifying the modular space of Calabi varieties is a challenging problem. So for a family of K3 surfaces over a punctured disk, Kolikov discovered that after a finite base change, there are degenerations with trivial canonical class. But this these are usually reducible, and there are infinitely many non-isomorphic ones. And the same framework, the same general framework holds in higher dimensions as well. There are degenerations with trivial canonical class and SLC singularities. I will define what is SLC, but usually infinitely many non-isomorphic ones. So a general approach to obtaining unique degenerations was first explored by Alexei for abelian varieties and Hacking for plane curves. So instead of just consider Calabi variety, one needs to work with pairs X and with a boundary epsilon H. This H is an ample divisor and epsilon is small enough. And X is a Calabi variety. And for maximum generality, we consider polarized log Calabi pairs. So this is a definition of polarized log Calabi pair. A polarized log Calabi pair consists of an SLC log Calabi pair X delta with an effective ample integral divisor such that X delta plus UN is SLC for any sufficiently small positive real numbers. This U is sufficiently small. It actually means that the support of this N does not contain the LC center of X delta. Does not contain any LC center. LC center is an image of LC place, and which is a divisor over X delta, whose discrepancy with respect to this X delta is -1. So because polarized log Calabi pair is naturally unbounded, so we need to fix some condition to make it bounded. So first we fix the dimension D and the CV be two positive rational number. A DCV polarized log Calabi pair is a polarized log Calabi pair X delta N such that the dimension equal to D and delta equal to CD for some integral divisor, which is equal to, say, the coefficient of delta is equal to C times the natural number, and the volume of is fixed equal to V. Notice that here we consider SLC log Calabi. SLC is short for semi-log canonical. When we study semi-log canonical, it is discovered by Colin and that in order to compactify the modular theory of higher dimensional varieties, we need SLC pairs. SLC pair is schemes that are S2 and whose codimension 1 points are either regular points or nodes. For example, in the modular space of elliptic curve, the degeneration of elliptic curve is not normal. It has the codimension 1 points of these degenerations are just nodes. And it is pretty interesting that for higher dimensional case to compactify it, we only need such pairs which has restriction only in codimension 1. And polarized log pairs have a natural modular space, which we denote by the PCY. So fix a rational number epsilon and consider those polarized Calabi pairs, for which X delta plus epsilon N is SLC. Then X delta plus epsilon N is a stable pair. So a pair we say is a stable pair if it has SLC singularity and is projective, and KX and the the canonical class of the total space is empty. The corresponding objects, because we can add a very small polarization to make it stable, then we have a natural embedding for the modular space of polarized Calabi pairs to the modular space of stable pairs. It is also known as a KSBA modular space. And it is proved by Collat and Xu that there is a modular space once we fix the DCV for all DCV polarized log Calabi pairs. But this modular space may have infinitely many components. So they can only show that it's every irreducible component of this modular space is projective. And Birka proved that this modular space is actually of finite type. Hence, it is the projective space itself is the modular space is projective. The finite modular space is finite type. It's equal to say that the set of varieties is bounded. So bounded means we say a set of varieties is bounded. If there is a projective morphism W to T, where T is of finite type, and such that for every variety in this set, there is a closed point and an isomorphism from a fiber to this X, from a fiber in this projective morphism. And we can also define birationally bounded if we replace this isomorphism by a birational map. And for pairs, we can also define log bounded. Log bounded is we add a boundary here, WD, and this isomorphism is an isomorphism of log pairs. The following theorem is due to Birka. It actually proves that all DCV polarized log Calabi pair is bounded. First, he proves that the fixed dimension D and the coefficient C and the volume V, then there exists a positive rational number T only depending on DCV, such that if X delta N is a DCV polarized log Calabi pair, then X delta plus Tn is a stable pair. This T is fixed, it has a lower bound. For general polarized log Calabi pair, we know there may be no lower bounds. It is possible that it is possible that no matter how small this T choose, it is not SLC, but it is a surprising result that once we fix this this DCV, there is a lower bound. And once this T is fixed, then we know the coefficient of the delta plus Tn is in a fixed set. And the volume of Kx plus delta plus Tn is bounded. Then we can use the result of boundedness of KSBA modular space, also known as Hagen-Magana-Xu. So the second theorem, which is almost an immediate consequence, is that the set of DCV polarized log Calabi pairs are log bounded. Now let's define what is a modular of polarized log Calabi pair. So now we know the elements in this modular should be DCV polarized Calabi. But to define it, we also need to define the functor precisely. So let S be a reduced scheme. A DCV polarized Calabi family, where S consists of a projective morphism of schemes, a Q divisor B and an integral divisor N on X, such that its X B plus UN to S is a stable family. A stable family is uh, it's locally stable and with relative ample total log canonical class. That is kx plus b plus un is ample over S. And locally stable is defined by Calabi for high-dimensional variety. It is the definition is pretty long and I will talk about it here. So it's a stable family of pure dimension D, and the coefficient of this B is infinite C, and Dn are relative manifold divisors. Manifold divisor is also a very you can consider it as it is defined for some big opens. It is defined on some big open subset, and on that relative big open subset, which is an open subset, and on each fiber it is big. On that open subset, it is Cartier, and it does not contain the irreducible component of any fiber. So that is relative manifold divisor. It is defined. It is defined in a way that its pullback where any base change is well defined. And the third is the relative log canonical class is relatively trivial. And for any fiber, the volume of the polarization is fixed equal to V. And then we define the modular functor on the category of reduced schemes is defined by this. The functor will transfer a reduced scheme S to the set of all DCV polarized Calabi families over X. And this functor has a projective cross modular space. Now, this is a mean result. The mean result is fixed dimension D, fixed coefficient set C, and will be the volume. Let X be a quasi-projective normal variety, and X delta to C be a family of projective log pairs of dimension D over a smooth curve, and C be a closed point. Suppose Kx plus delta is relatively trivial, and suppose a special fiber is an SLC pair. Then there is a divisor, and suppose that there is a divisor N on X such that the general fiber is a DCV polarized log Calabi pair. Then every irreducible component of the special fiber is birationally bounded. It's birationally equivalent to a fiber of a projective morphism, which depending only on DCV. And a particular case of polarized Calabi pair is that of final pairs, polarized by effective anti-polarly canonical divisors. That is, final pairs will naturally lead to a polarized log Calabi pair. The next theorem is due to Professor Birka. First, let's see what it is. So fix the dimension D and fix the coefficient set C. Then there exists a natural number N depending only on D and C, satisfying the following. Suppose XB is an LC pair of dimension D and XA is a contraction subset B equals to CD for integral divisor B. And the negative kx plus B is ample over there. Then for any point, any closed point, there is a Q divisor B prime greater or equal to B such that n kx plus B is linearly equivalent to 0 over there. This is not Q linearly equivalent, it's linearly equivalent. And xb is LC over a neighborhood of Z. Oh, sorry, there is a typo. Here it should be B prime, B prime. This B prime is also called the complement of X, or the relative complement. Here, as we can see, because nkx plus B prime is linearly equivalent to 0 over Z, then the coefficient, in particular, the coefficient of B prime should be some natural number over n. So n times B prime is integral. So with this theorem, we can construct a relative log Calabi, we can construct a log Calabi family. And for the polarization, suppose with the same notation as in this theorem, suppose xb is epsilon LC, then a general fiber is epsilon log canonical. It's epsilon LC final. Epsilon LC means the discrepancy is greater or equal to -1 plus epsilon. And a general fiber, then by the Birka-BAB theorem, xj delta j is in a log bounded family, and there exists an M such that kxu plus bu is relatively ample over an open subset, and this M is depending only on d and epsilon. Then we choose a general element in this linear system. We let it to be n. Nu, and let n to be the closure of Nu. Then this n naturally gives a polarization on the general fiber. So with this, we have the corollary. The main theorem is about the polarized log Calabi fibration. The corollary is about final fibration. So again, we fix the dimension d, and we fix the coefficient c, and the epsilon be a positive rational number. Let x be a quasi-projective normal variety, and x delta be a family of projective log pairs of dimension d over a smooth curve, and c be a closed point. Suppose delta equal to cd for an integral divisor b, and negative kx plus delta is ample over c. And the special fiber is an SLC pair. And the general fiber is the epsilon log canonical. Then every irreducible component of the special fiber is birationally bounded. Note that in the above two results, we assume kx plus delta is Q Cartier. In the first one, we assume it's Q linearly equal to 0. The second, we assume is relatively anti-ample. Both are Q Cartier. This is because unexpected jumps of Cordillera dimension happen precisely when the canonical class of the total space is not Q Cartier. Let's see an example. This example shows that how do we have jump of Cordillera dimension. So let R be the image of the embedding of P1 into P4 by the global sections of O4, and the T be the image of the embedding of P1 times P1 into P5 by the global section. Then one can show that this R is actually a hyperplane section, in a general hyperplane section in T. And then we define CR to be the projectivized cone over R, and CT is a projectivized cone over T. Then because R is a general hyperplane section in T, then this CR is a general hyperplane section in CT. And also, it is easy to say that T is also a hyperplane section of CT. So we know that both T and CR are hyperplane sections of CT. But on the other hand, let W be a closed subvariety in P5 times A1 in the quasi-projective threefold defined here. Then we know that this morphism, this natural projection, gives us a family of surfaces. When T equal to 0, this is U to 4, U to 3 times V, U to U square V square, U V cubic, V to 4, and W to 4. Then this W0 is isomorphic to CR. And when T equal to 1, we can see W1 is isomorphic to the embedding of P2 into P5 by the global section of P22. Then we know that P2, and then from these two examples, we see that P2 and P1 times P1 have the same deformation type. This is not good because in the first deformation, the canonical class of the total space is not Q-Cartesian. And also, so that's why we need to assume the canonical class is Q-Cartesian. And also in the theorem, we only talk about the birational boundedness of the spatial fiber. This is because birational boundedness may be the best one can hope, because there are examples that the spatial fiber is not bounded. This is one example. So Hacking and Prokhorov show that for any triple pair of natural number ABC, such as a squared plus b squared plus c squared equals 3 ABC, it is also known as a Markov equation. There exists a morphism x to t over a smooth curve germ zero, such that kx is Q-Cartesian. Xt is isomorphic to P2 for any t non-zero, and x0 is isomorphic to the weighted projective space ABC. And the function, because the function has infinitely many positive integer solutions, the spatial fiber is not bounded clearly, but they are all birationally equivalent to P2. So that's why birationally bounded seems to be the best result one can hope. And another thing is that here we say every irreducible component of Xc. It is natural to ask, can we bound the number of irreducible components? The answer is no. The following example shows that there may be arbitrarily many components in the central fiber. So let X delta to C be a family of log pairs over a smooth curve satisfying the assumptions. Suppose the central fiber has more than 2 irreducible components. Note that every irreducible component Xc is an LC center of X delta plus Xc. Then there are two LC places. There are at least 2 LC places contained in the central fiber, and they intersect each other. LC places is a divisors with coefficient equal to 1. Then we can blow up their intersection. We get more divisor. And we keep blowing up. We can see that X, there are infinitely many divisors over X, whose discrepancy with respect to this pair is -1. So then for any M, we can blow up and M divisors with coefficients equal to 1. And suppose notice that once we blow up, the multiplicity of the central fiber may no longer be 1. But we can do a ramified cover to make the multiplicity equal to 1. This part is known as a Kalamata trick. Let me use a figure to explain this. So suppose the blue square, this is X. And for the central fiber, we have two components. Then the intersection of these two components is again an LC center. We can blow up it and we have a new divisor, and this divisor has coefficient 1. And notice that the multiplicity of this new divisor is equal to the multiplicity of this one plus this one. Suppose these two are reduced, then the multiplicity will be 2. But after a finite cover, it will be 1. So this is a figure to explain why we can reduce the multiplicity. Suppose we have a finite a ramified cover here, and then we use another ramified cover. Once we do fiber product, we will have this. This is obviously non-normal. And if we do normalization, then we have two components. For each component, the multiplicity from this new one to here will become just 1. Okay. Any question? No questions. Let's continue. Now I want to talk about the proof of this theorem. The main tools used in this paper are the modular space of polarized log Calabi pairs and the semi-stable reduction. So we use the same notation. Because the general fiber is a DCV polarized log Calabi pair, we can construct a modular map. Here U is an open subset and S is a modular space, U to S. And because this S is proper, it's actually projective. The modular space, the modular map from U to S can be extended to morphism C to S after a finite base change. Then the pullback of the universal family. Here, universal family adds this. This is because this DCV polarized log Calabi modular, it's actually a cos modular space. It is not a fine modular space. But the good thing is, it is a quotient of some fine modular space coming from the Hilbert scheme. In the construction of the modular of polarized Calabi pair, Professor Birka used the same technique as in the construction of KSBA modular. Both are construct some strongly embedded pairs. That is a family with embedding into Pn, and then consider it as a subscheme in the Hilbert scheme, and then do quotient. Anyway, we can after a finite base change, we can talk about the universal family. And the pullback from the universal family through the modular morphism will define a new fibration. And X prime, delta prime to C. And the fibers of this new fibration are all DCV polarized log Calabi pair. In particular, the central fiber of the new fibration is log bounded. And because the original vibration and the new vibration, they are both long-Calabi vibration over the same, and they have the same generic fiber. Then they are frequently birationally equivalent. Frequently birationally equivalent means there is a common log resolution y to x and to sorry, there is a typo. It should be x prime, such that ky plus delta y is equal to the pullback of kx plus delta, and also equal to the pullback of kx prime plus delta prime. So therefore, any irreducible component of xc on x prime is an LC place of x prime delta prime plus c prime. This is because since they are birationally equivalent. For any divisor over x or over x prime, the discrepancy with respect to x delta is equal to the discrepancy with respect to x prime delta prime. So xc is clearly LC place of x delta plus xc. So it's actually LC also an LC place of x prime delta prime plus xc prime. So note that LC center of x prime delta prime plus xc prime contained in the central fiber is also an LC center of the central fiber by subarc junction. So the main difficulty is to use the boundedness of LC centers because the central fiber it's DCV polarized log Calabi pair. So it's naturally in a log bounded so it's naturally log bounded, and it is we can see that all LC centers in this log bounded family is also bounded. So we know the image of xc in x prime is in a bounded, it's bounded, but the difficulty is to use the boundedness of its image to prove the birational boundedness of itself. This is because the contraction from the exceptional divisor to its image cannot be controlled in general. So now let's consider the following very good case.
Sorry,
suppose
I have a question.
Yes.
So if in your Krepan map, from your original family to the universal family, some divisor on the central fiber are contracted. How do you control the birationally boundedness of this component?
You mean from x to x prime?
Yes.
I'm going to talk about this.
Okay.
We can control its image on x prime, right? So yeah, let's consider the following very good case. Suppose this x prime delta prime plus xc prime is log smooth. Then every LC center of it is a stratum of this. A stratum is an irreducible component of the intersection of some prime divisors of this. So blowing up the stratum will extract an LC place, and because it is smooth, such blow up is just the PR bundle over the image, where R is a relative dimension. So if we have this, then once we know that the image of the divisor is bounded, then its PR bundle is clearly bounded, clearly birationally bounded. Then we know the result. So this is a very good case, but unluckily, because this x prime delta prime plus xc prime is a pullback of the universal family. So unfortunately, we cannot modify the universal family like taking a fiberized log resolution, so that pullback via any morphism is log smooth. We can also modify the universal family to make the case very good. But a good thing is that we can use semi-stable reduction to make singularities locally toric. This here is analytically locally. And for toric case, such contraction from the exceptional divisor to its image is well understood according to the following result. This result is due to Professor Hu, Liu, and Yao. So let x sig prime to x sigma be a toric morphism induced by a refinement of phase. Then the fiber of actually they proved this result for any toric morphism. And here we only need to consider refinement of phase because for toric case we can resolve the singularity by taking refinement of the phase. Then the fiber of this toric morphism over a point depends only on the orbit that contains its point. Denote this fiber by f sigma. Then this fiber can be described as follows. So we define sigma prime to be the set of points whose interior is mapped to the interior of sigma. Then the inverse image of y is equal to f sigma. And this is a connected reducible toric variety, whose irreducible components are the toric varieties associated to the relative star of the primitive elements. So here it contains many terms from toric geometry. But roughly speaking, it says if x prime to x is a toric birational morphism, and P is a prime F exceptional divisor, then P is birationally equivalent to the PR bundle over its image. So this figure it's compares what is the relative star. Toroidal pairs is analytically toric. So given a normal variety and a reduced divisor, we call XD a toroidal pair if for every closed point there exists a toric variety and a point in this toric variety, and an isomorphism of complete local algebra, such that the ideal of D maps isomorphically to the ideal of X sigma set minus T sigma. This T sigma is a big torus. A dominant, so this is called a toroidal pair. A dominant morphism between toroidal pairs is called toroidal morphism if for every closed point X, there exist local models. And there exist two local models and a toric morphism so that the following diagram commutes. Given a toroidal morphism between projective toroidal pairs with connected fibers, we say F is weakly semi-stable if F is equidimensional and all the fibers of the morphism are reduced and the base is non-singular. This is weakly semi-stable. And if X is also smooth, we call F is semi-stable. And the following is a lemma. This lemma says, given a weakly semi-stable morphism and C to S to be a morphism from a smooth variety to the space S, such that the inverse image of ds is a normal crossing divisor. Then the pullback, the base change of this F via J will give us a new semi-stable morphism. Okay. In particular, let X prime be the fiber product, and dx prime be the inverse image of D in X prime, then then this X prime dx prime is a toroidal pair. As you can see, we are going to use so suppose this X to S is the universal family, and the C to S is a modular space. It's a modular map. Then the pullback via this modular map will give us then this X prime will have the toroidal pair, that is locally it has toric singularity. So things will be very good. So the only problem is if whether we can modify this universal family to make it a weakly semistable. Luckily, we have the following result. It is called semistable reduction. In 2000, Aberwood and Caro proved that any dominant morphism of varieties of characteristic 0 can be made weakly semistable by replacing S by a smooth alternation. A smooth alternation is a generically finite cover. And replacing the proper transform of X by a modification, that is X prime has a birational contraction to the mean component of the fiber product, X times S prime over S. So moreover, they formulate a stronger conjecture that this new morphism can be made semi-stable. And in 2019, Karim, Gaku, and Michael Tamkin solved the semi-stable reduction conjecture. So this is their result. So let X to Z be a projective morphism between projective normal varieties, and D is a closed subset. Then there exists a projective, surjective, generically finite morphism of irreducible varieties. Z prime to Z, a projective birational morphism of irreducible varieties. X prime to the mean component of the fiber product. And two divisors B prime in Z prime and D prime, such that this D prime contains the fiber product, the inverse image of D, and the inverse image of B prime. And second is that the morphism is semi-stable. So now we can complete our proof. Suppose this curved X, curved D, this is two curved S is a universal family. Then after a semi-stable reduction, we can we have a semi-stable morphism, curved X prime, curved D prime, curved S prime. And suppose this is a modular map from C to here. Then the pullback is weakly semi-stable. In particular, this X prime, this is a toroidal pair. Then it has a toric singularity locally. And therefore, an LC place is birationally equivalent to a PR bundle over the corresponding LC center. So now we can complete the proof. But note that in the argument, we take a ramified cover of the base. By Harris formula, the preimage of an LC center is still an LC center. The following theorem tells about the discrepancies and finite morphisms. Given an LC pair and a ramified cover, and the delta prime be a Q divisor such that there is a canonical linear equivalent class. Suppose E is a prime divisor over X and F is a prime divisor over X prime dominant in E. Then the log discrepancy of F is equal to the ramified index of F times the log discrepancy of E. In particular, if 1 is 0, that means if it is an LC place, 1 is 0, then another is also 0. So we have a more general theorem, but a little bit technical. So fix the dimension and the coefficients and volume. Then there exist two natural numbers, M and Z, and contractions. Wi to Ti, where Ti is this I is from 0 to D minus 1. Where Ti is finite type and the relative dimension is satisfying the following. Suppose X is quasi-projective. X to C is a fibration. Here we only need it to be a fibration, not a family of log pairs. Such that it's relatively trivial, and the special fiber is sorry, it seems we do not need the second one. Here is a typo. And there exists a divisor N on X such that the general fiber is a DCV polarized log Calabi pair. If we let T to be the log canonical threshold is the maximum number T such that X delta plus TC is still log canonical. Suppose P is an LC place of this X delta plus TXC. Note that if it is note that in the mean theorem, this T is 1. It's just 1. So suppose P is an LC place of this dominant C. Then there is a finite dominant map. P D minus 1 minus I times WTI to P for some closed points Ti. And the degree of the dominant map is less or equal to the minimum of the multiplicity of P and M. And furthermore, the number of not uniroot irreducible components of Xc is less than N. Although we cannot control the number of all irreducible components of the central fiber, but we can control the number of not uniroot irreducible components of the central fiber. Okay. Any question?
Can you actually have more than 2 non-uniroot components if the total is
Yes. Yes, we can. I don't know any example, but I'm sure there is more than 2. There is more than 2 irreducible components. Maybe more than 2.
I mean, for when you degenerate hyperkähler, for instance, you cannot have only one component that is non-uniroot.
So I didn't hear you.
Sorry? I was saying that when you take family of hyperkähler and you degenerate it on the central fiber, you can have at most one component that is non-uniroot.
There's only one not uniroot component
on the central fiber, exactly.
Oh.
So I mean, the less than is less than N, but maybe N is 1.
Okay. I don't know this result before. You mean there is exactly one not uniroot component?
For hyperkähler, yes. For Calabi, also.
That's interesting. Sorry, I don't know this result.
Yeah, we can go on.
Next, I want to talk about why I consider this theorem. This is because I want to actually I want to study the singularity of final fibrations. I want to control the multiplicity of the central fiber. But in some sense, I failed. even if I can prove the birational boundedness of the central fiber, I cannot get the boundedness of multiplicity. And the boundedness of the multiplicity is closely related to the following theory. It is a conjecture in last year, but recently it is proved by Professor Birka. It is known as a Shorthoff-McCulloch conjecture. So fix the dimension d and epsilon be a positive rational number. Then there exists a delta depending only on b epsilon satisfying the following. So let xb be a pair where b is a Q boundary. And F be a contraction such that the total space is epsilon log canonical, relative dimension equal to p, and kx plus b is relatively trivial over Z, and negative kx is big over Z. Then the generalized pair induced by the canonical bundle formula is generalized delta LC. So that's all I want to talk about today. Thank you. Any questions?